Hello everyone, welcome back to Nated Engineering. Today we are doing chems under mechanical drafting and form. So before we start, so that I do not get any trouble of viewing something that is not mine or displaying something that is not mine on my channel, the link to the website that I'm currently in now will be displayed in your screen, and you can also find it in the description box. So we are going to continue. What exactly is a chem? So a chem is exactly what you see on your screen. It's a mechanism that we use to convert from rotary motion to linear motion. A chem will consist of two parts. We're having this part here which is moving up and down. We call that a chem follower. And we have this part that it's rotating. We call that a chem profile. So an example where we are going to use a chem, it's on your IC engine. On your IC engine, we know we need the inlet valve and outlet valve to close and open at specific times, at specific strokes of the internal combustion process. We are going to use a chem to time those opening and closing of the valves. We know that when it comes to the inlet valve, we want it to be open during induction, but we want it to be closed during power stroke, compression stroke, and the exhaust stroke. And when it comes to the outlet valve, we want it to be open during the exhaust stroke, but we want it to be closed during the induction power and compression stroke. So we are going to use a chem to control that motion. This object, this follower, which is the one that is moving up and down, will be the one which is opening and closing the valve. Let's say as it is going up, it is closing the valve, and as it is going down, it is opening the valve. So on this topic, what we are going to do is we will be drawing what we call a displacement diagram and a chem profile. A displacement diagram is the path that we want the chem follower to take. And that displacement diagram, we will then use it to construct or to find what shape will the chem profile be for us to be able to achieve that motion that we want the chem follower to follow. So from here, we are going to start with drawing the displacement diagram. We are only going to cover displacement diagram on this lesson. So we have three motions. We have the constant velocity, we have the simple harmonic, we have the uniform acceleration and retardation. So we are going to draw a displacement diagram for each and every one of the three, so that we see how they differ from each other. We're going to start with constant velocity. I'm going to put it down as CV. We're going to start with the constant velocity. So to draw the displacement diagram, we are going to need a stroke height. The stroke height is not shown on the question that is on the screen now, because I only took this part of the question, the performance part of it. So I'm going to use a stroke height of 50. A stroke height, it's the stroke height of the follower, the distance which it moves up and down. Our stroke height is what? It's 50. And I'm also going to draw a horizontal line of 120 and close this so that I have a rectangle. So what I need to do now is to divide this line, our stroke height, into 6 equal spaces. So if you're doing this on AutoCAD, it's easy. Just say div, press enter. You say select object to select object and say I want 6 equal spaces. As you can see, we are now having 1, 2, 3, 4, 5, 6 spaces. But you do not have that privilege when we are using a drawing board. So on a drawing board, we are going to draw a line from this point at any angle. And that line must be 60 millimeters. Why 60 millimeters? Is because we want 6 equal spaces. So what we are going to do is we are going to divide this line into 10, let's say div, it says select, say I want 6 divisions. So if you are using a drawing board, we are going, since this line is 60 millimeters, we are going to divide this line by 10. So we are going to have 6 spaces, and the distance between those points, it's 10 millimeter, 10 millimeter, 10 millimeters. Why are we doing the divisions on this line instead of doing it straight here? It's because we are using 50, and if you say 60 divided by 6, we are going to have to get 8.333. So it's kind of impossible to measure 8.33 with a ruler. So what we are going to do is we are going to let this line help us with the division. So what we need to do now is to join the last point with this point, and then from here, with the help of our set squares, we are going to draw a line at each and every division that we made on this line, and those lines must be parallel to the first line that we draw. So it's going to be something like this. So if I highlight the divisions that I made here before, you can see that they go straight to those divisions. So in this way, we are able to get 6 equal, accurately spaced divisions. And then from there, we are going to draw and then we said our vertical line is what? It's 120. So we know a rotation, a full rotation, is 360 degrees. So what we are going to do is we are going to take our circle and divide it into 12 equal spaces. Those 12 equal spaces must be represented here. So what I'm saying is we are going to divide this line into 12 equal spaces. With this one, it's easy because the length of this line is 120. So you can just divide it by 10 millimeters, 10 millimeters. So we can check. You see the distance between those lines is 10 millimeters. So it's easy to measure 10 in your ruler. For this one, you don't need an external line to help you with the divisions. And then from there, we have to label. So we're going to label here. From the start, it will be 0 degrees. And then from here, I'm going to label the bottom here. That will be representing 1 revolution. And the scale 10 millimeters, it's equals to 30 degrees. And then I'm also going to label this side from here. That will be rise, stroke, fall. So this, I'm going to change all of this into the construction there. This is construction. You're going to use your 0.3 on your drawing board to draw this. It's construction. So now we are going to construct what they are telling us to construct here. So they are saying from 0 to 180, the lift occurs from 0 to 180. We are using what? Constant volume. So from 0 to 180, which will be here, it will be constant volume, which it's a straight line up. And then they say from 180 to 270, it dwells. So it will be dwelling here. We're just going to have a horizontal line. And then they say end fall occur from 270 to 360, which will be something like that. And then we have to create extra divisions here. Those divisions are going to help us when we are now drawing the divisions are going to help us when we are now drawing the chem profile, because we know that this is still the displacement diagram. So this is how a displacement diagram of a simple of a constant velocity will look like. We are going to look at the next one, which will be, let's name it, it's going to be simple harmonic. It's simple harmonic motion. So the constructions are now slightly different from what we were doing. So yes, we are still going to have the 50. We just change this to construction. It's 9. We're still going to have the 50 as our stroke length. The stroke length will be given always. You don't use 50 all of the time. We're going to use our 120, but 120, it's always like that. So with simple harmonic motion, we still need 6 divisions, but we are not going to divide our stroke height the same way we did when we were dealing with constant volume. And they are not going to be equal. The divisions are not going to be equal. So what we're going to do is we're going to draw a circle, a semicircle actually, like this. So you are going to draw a semicircle from this point to this point using this as your center, which is half of the stroke length. I'm going to trim this out. You only need this part of it. And then from there, you are going to divide. I'll make sure it's annotated. You are going to use your 80 degrees, 60 degrees set square. I'm going to make divisions like this. And then now we are having something like this. So remember what they are saying. In this case, it's simple harmonic. They say lift occurs from 0 to 180, and then from 180 to 270 it dwells, and falls from 270 to 360. So what we are going to do is we are going to have our simple harmonic motion from 0 to 180. Now, we are no longer using a straight line like we did in a constant volume. So, in my case, I'm going to use the spline command. When you're using a drawing board, we are going to use a flexi curve. So, in a flexi curve, we are going to start from here. Let me change my layout. You know you have to start from 0, and we are going to end up where 180. So, you are going to join this line with this line, this line, this line, this line, this line, and this line. You know, we ended up in where 180, and then it will be like that. And then from here to where to 270, they said what? It's going to 12. And then now we have to draw our spline again. We have to draw our line from this point to this point. We have to divide this portion from 270 to 360. Just the same thing that we did on our constant volume. We're going to divide, make extra divisions of 5 millimeters. And from there, I can now draw the spline from here. The second point is this one, this one, this one, this one, up until we get to 360. And that one is simple harmonic. And then the last one will be what? Uniform acceleration and retardation. I'm going to put it down here. Uniform acceleration, uniform acceleration and retardation. So because now the construction is the same for this two, I'm going to copy this one. And copy. Anyway, put it here. The construction will be the same for the constant volume and uniform acceleration. I'm just only going to erase this. So what we have now is from 0 to 180, that it's our lift. Only now it's not going to take place using constant velocity. It's not going to take place using simple harmonic motion, but it's going to take place using what? Uniform acceleration and retardation. So what we are going to do is, this is where we are starting, and this is where we are going to end. We are going to draw this. Let me use another color. Let me use this color. Join that point where we are going to start and where you are going to finish. Join those 2 points. And which one is the center? The center is it's 90 degrees. So we are going to do from where we're starting 90, we draw this line. Another one from where we're starting 90, we draw this line. And then we come where we are going to end, which is 180, where we are going to end to 90. Again, we draw another line, and this is how we're going to, this is our construction. Then we are using the spline again. If you are using a drawing board, that will be your flexi curve. We start, let me change my layout. We start from point 0, and then we go to the second line. Where this first line, the first one from the bottom, is cutting our first vertical line, we are going to put, that will be our point there. We go to the second vertical line, that's 1, 2, the second vertical line. Now we are using the second line from the bottom, it's 1, it's 2. Where it is cutting our vertical line, we are also going to make that a point. And then it will be this one now, where the long one is cutting 90 degrees, or the long one is cutting the middle line, the middle vertical line. That one will also be our point. We're going to put, we're making it a point, basically. So, same thing. We're coming to this line now. We want it where it is being cut by this line, which will be here. And then, same thing here. And then where we are going to end. And that will be our rise. And then they say it's going to what? Dwell from 180 to 270, which will be that one. Fortunately enough, we already divided this one into, we need 6 spaces basically. It will be 1, 2, 3, 4, 5, 6. So what do we do? Because we know that the fall, it's uniform acceleration and retardation. We join where we are coming from and where we are going. And those are our 3 motion that we have. So that's it for this video. I will see you on the next video where we are going to construct the actual cam profile using these diagrams.